All right, here is part 2, and case control studies are another observational study. And again, we've got a population, we've got cases, people with the disease, we've got controls, people without the disease, and then we go back in time to look and see potential exposures and what the proportion of those exposures are. I like this figure here because it helps us to think about the relationship between a prospective cohort and a retrospective cohort in case control study. Now, both of these, we are looking into the past, but they are different. Here, we've got a cohort, similar people. Here, we have cases and controls. So there is a difference. If you've got questions on understanding the difference between these two, please make sure to let me know. I think a great way to think about cases and controls are to think about things like cancer. You would assemble all the individuals with a particular cancer diagnosis in the cases. And then maybe from that same hospital, you would find age-matched controls, people that do not have the cancer, and then you would go back in time to look to see what the proportion of a particular risk factor is in each group, whether that be cigarette smoking, exposure to agricultural chemicals, things like that. Again, here, a great example is we've got falls. People in a skilled nursing facility, and we go back in time to see what the potential risk factors could be. How do we categorize them? And then that gives us a proportion in each group that experienced the fall. Here are some ways to express and compare risk. Absolute risk is the probability of an event in a population under study. The value is the same as incidence. So these terms are often interchangeable. We'll utilize the word incidence throughout the term. The absolute risk is the number of new cases over a period of time divided by the number of people in the group. For example, the death rate or absolute risk of lung cancer in smokers is 341 per 100,000 years. The death rate, the absolute risk of lung cancer in non-smokers, is only 14.7 per 100,000 years. The attributable risk. So what is the additional risk of disease following exposure over and above that experienced by people who are not exposed? The answer is expressed as the attributable risk, the absolute risk of disease in exposed persons minus the absolute risk in non-exposed persons. So let's take a look here with our smoking example. So we minus 14.7 from 341. The attributable risk, also known as the risk difference, in this case is 326.6 per 100,000 years. Relative risk. How many times more likely are exposed persons to get the disease or to experience the injury relative to non-exposed persons? This is the relative risk or risk ratio. We'll look at how this is calculated. Nobody does the math. We've got computers to do that, statistical software, but if you wanted to do the math, you would set up a 2x2 contingency table or 2x2 standard table. The disease or injury would go across the top. Yes and no, and then the risk factor, yes and no, as you observe there. And then you would put in the number in each box that either had the disease and whether or not they possess the risk factor, or didn't have the disease, and whether or not they had the risk factor. So this is used in cohort studies. And you can see the formula there. Again, that formula is based upon the 2x2 table. Here's the important information regarding relative risk. Relative risk of 1.0 indicates that the incidence rates of disease or injury in the exposed and non-exposed groups are identical, and thus there is no association observed between exposure and the disease in the data. But if you run the numbers and you get a value greater than 1.0, indicating a positive association or an increased risk. So if your analysis found that the relative risk was 2.2 and it was statistically significant, you would say that the individuals in the at-risk group were 2.2 times more likely to experience the disease or injury than those in the reference group. The key here, and to go back a few slides, whatever you put as the risk factor across the top here, that is the risk, what you're hypothesizing as what will increase the risk for somebody. So let's say you got a relative risk that was less than 1.0. This is an inverse association or a decreased risk. So let's say you got a relative risk of 0.25. Well, since it's below 1.0, that means there was a protective effect. So the group that you hypothesized were going to be at risk based upon a particular risk factor, they actually were at a lesser risk. I've had that happen before, and it's kind of surprising when you get it that first time. Now in tables, investigators will list the 1.0 value as the value for the comparison group or the reference group. So that illustrates, when you look at a table and you see 1.0, that means that's the reference group, and then the other group is the at-risk group, which you're then looking to see, was it above or below 1.0, and was it statistically significant? Here's a math example and how you would lay things out. Let's say you are looking at risk of sudden death in those who are excessive exercisers versus those who are moderate exercisers. You would plug in the numbers and run the data, and you'd find that those in the excessive exerciser group were 6.7 times more likely to experience sudden death than moderate exercisers. So that would be an example of relative risk or the risk ratio. You can also calculate relative risk using incidence data. And our number here is going to be similar yet different. So here our number was 6.71. Now that we add in the person years, we get 7.56. They are similar, but using incidence density provides a more accurate assessment of risk than when using cumulative incidence estimates. So how did we come up with the numbers here, the 6.8 and 0.9? So to do this, you take 16 divided by the person years, and then you round it. So it's based upon 1,000 person years. Same thing here, 5 divided by this number gives you 0.9. Or I would say 0.0009, and then you round it. Population risk. How much does a risk factor contribute to the overall rates of disease in groups of people rather than individuals? Important for determining risk factors and identifying which are trivial for the overall health of a population. The population attributable fraction is fraction of disease occurrence in a population associated with a particular risk factor. So it's the population attributable risk divided by the total incidence of disease in the population. So if you really got excited about epidemiology and you thought, okay, after I'm done with my PhD, I'm going to go get a master's in public health and epidemiology, we would get more into these types of things. We're not going to really spend any time with this stuff at all. Now, it's important that you take other variables into account because many other variables are involved beyond just the exposure and the disease. Other variables can cause unwanted artificial change in the observed relationship between exposure and disease. This is confounding, leading to incorrect conclusions about the relationship. I think I talked previously about if you were doing a study and you were thinking that coffee drinking led to lung cancer. But if you didn't take into account that maybe people, when they were drinking coffee, also enjoyed cigarette smoking, you would have missed that relationship. These other variables, they can also modify the magnitude of the exposure-disease relationship. This is known as effect modification. Variables that are part of a system being studied but are not the exposure and the disease of primary interest are extraneous variables. For example, if you looked at the study of exercise and sudden death, the extraneous variables could be age, BMI, coexisting diseases, and the presence of cardiovascular disease risk factors. Another term for extraneous variables are covariates. I talked about relative risk. What about the odds ratios? We'll talk more about that in the next lecture. The odds ratios are sometimes used interchangeably with the relative risk. Shouldn't be. The odds ratios should be for case control, but the odds ratios will be used for prospective and retrospective studies when you're looking at crude measures of effect and adjusted measures. So the crude measures of effect are just that. What are the odds of somebody getting injured based upon how strong they are in the preseason? An adjusted odds ratio, this adjusted measure, takes into account other variables that might affect that relationship. And so here's an example. Dr. Phil Plisky, who was a graduate of Rocky Mountain University from its early days, he, if you take a look at table 6 in his study, had the AOR. What's that mean? That's the abbreviation there for adjusted odds ratio. He also had crude odds ratios, and we find those in table 5, the OR here. All right, that is the end of lecture 4.1. When you're ready, move on to 4.2.